All right. Welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, but if you have questions, you can unmute and ask questions or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. Okay, that's about it. Now let me briefly introduce our speaker today. It is an honor to host Dr. Borku Baikal, who is an assistant professor in the Department of Chemical Biomolecular Engineering and a resident faculty in the Center for Clean Energy Engineering at University of Connecticut. She holds a bachelor's degree in chemical and biological engineering from Koch University, in master's degree in chemical engineering from Carnegie Mellon University, and PhD degree in chemical engineering from Texas A&M University. Before joining University of Connecticut, Borku was a postdoctoral research associate at the Texas A&M Energy Institute. Her research focuses on data-centric process systems engineering and machine learning of energy-critical systems spanning chemical, environmental, and biological domains. Among her awards are the American Chemical Society Petroleum Research Fund Doctoral New Investigator Award, the 2020 CAST Directors Award, and the Outstanding Graduate Student Award from Texas A&M. She was also selected as a rising star in chemical engineering by the Massachusetts, the MIT in 2019. Today, she will talk about a data-driven process systems engineering approach for supply chain management and enterprise-wide optimization. Please enjoy and expect a wonderful talk. Now, let me ask one question to Borku just to get to know her better and to make this seminar somewhat informal. Okay, here's question. You ready?
Yes.
All right. Obviously, you are passionate about data-driven, method and numerical optimization. What aspects of them fascinates and excites you?
It really, I think the endless opportunities. Every single day, I'm discovering something new about them and how we can use them in a more clear way or on a more clever way. I think the power with data is really really big, and it really is going to shape our lives in a more different way in the upcoming decades, I guess.
Yeah, I think that's how everyone feels these days, right? Thank you so much. The stage is yours.
Thank you so much for the very kind introduction, and thank you so much for the invitation as well. It is an honor to be here and to present what we have been working in the past couple of years. And also, I was mentioning this before everyone joined, but I did see a couple of mentors that presented in the seminar series, so that makes this presentation a little extra special for me and exciting for me. Today, I'm going to talk about data-driven optimization mainly, and how we can use data-driven optimization to address very tailored and very difficult types of problems, and the problems that we see mainly in supply chain management and enterprise-wide optimization type of problems. But before going into that, I am a chemical engineer by training, so I do want to start by sort of motivating why process systems engineering is a bit important to address this problem. So as chemical engineers, we design and operate chemical processes, and these chemical processes could be shown in block diagrams or process flow sheets. And what the idea essentially here is that you start from a raw material, you go through a series of processing units, and you're trying to get to this final product. And as you can see, there's this selected route, but there are many different routes in the background that exist. So the natural question becomes is that for example, which one is the most profitable one, which one is the most sustainable one. If I selected one route, what are my operating conditions for each of these unit operations? What's my temperature? What's my pressure? And generally the question is the process safe? So inherently, this is a decision-making problem. And the reality of that is you cannot implement all these alternatives in real life. So think of you trying to design a reactor. It's not really safe or really sound to create one reactor with like 5-liter reactor, then go to 10 liters, then to 15 liters, and play around with temperature and pressure and see what really sticks. So what we do is we take these chemical design and operation problems and represent them with mathematical models. And these mathematical models are going to entail our first principles of mass, energy, momentum balances. So we will be following physics. We can have process constraints that we don't want to violate. So for example, temperature of a reactor shouldn't maybe exceeding some value due to safety considerations. And we will always have some degrees of freedom, like our decision variables could be operating conditions, design considerations, and many other things. When these are attached to goals, now they become an optimization problem. And we can try to minimize CO2 emissions. We can have different objectives. For example, for the reactor example, you may want to maximize your yield. You may want to maximize your profit. But more formally, these optimization problems are given in this canonical form. So assuming that we have bounded decision variables, we can have a very nonlinear, non-convex objective function. We can have linear constraints or nonlinear constraints. And what we do is we look at the intersection of this feasible region, evaluate our objective function, and we can pinpoint where our optimal solution is. Now, this example is one-dimensional, it's pictorial, and we can plot everything and pinpoint where the optimal solution is at. But more formally, what you do is you can do the active set approach. So for example, we have two decision variables in this toy optimization problem. We have quadratic objective with linear constraints. And what you do with the active set approach is that you assume no active constraints and you write your Lagrangian, which is going to be essentially your objective function. Then what you do is you calculate the gradient of the Lagrangian and you solve for x1 and x2. So you have two equations, two unknowns, and you get some values for your decision variables. Then what you do is you go and check your constraint violations. So in this case, constraints 2, 3, and 4 are satisfied, but constraint 1 is violated. So what we need to do is go back and take this constraint as active. So now our Lagrangian considers the objective function and our active constraint. We take the gradient, make it equal to 0. We have 3 equations, 3 unknowns. So we have the 2 decision variables and our Lagrange multiplier. And then we check our constraint violations. Our first constraint is active, so we satisfy that. The second, third, and fourth are also satisfied. And our Lagrange multiplier is greater than or equal to 0. So we say that we found the solution. Now, this is obviously a very quick intro to fundamentals of optimization, but there's only one information I would like you to take from it, and that is to find the optimal solution, you need the gradient information. And the problems that we are actually working on today, this gradient information or this derivative information is not very easy to come by. So first of all, we're using increasingly complex simulation software, so we can capture the underlying physics much, much better due to the increasing computation power. But that means that we're expressing our systems with ordinary differential equations, or worse, a set of partial differential equations. And when you're trying to do this type of active set approach, it's not very trivial to find the gradient of a set of ODEs. You actually need to treat them to be able to use deterministic methods. So there's a challenge with regards to the complexity of the models we have. Second, we're interested in solving multi-scale design problems. These design problems can span over multiple temporal and spatial scales. So you can start from atomistic level calculations and go up to the supply chain analysis. And because you need to integrate these different temporal and spatial scales to your models, again, you have a very complicated mathematical system at the end that is not very easy to solve. And third, we have explosion of data. We would like to gain insights from data. Data is now very powerful for decision making, but we want to be able to use this information. And in all these three cases, that you will notice the derivatives of objectives or the constraints that we absolutely needed to be able to find the optimal solution is going to be partially available, totally intractable, or the problem is going to be very hard to solve using deterministic methods. And this third bullet point, this hard to solve, is quite important because that really motivates us with our enterprise-wide optimization or supply chain management type of problems. So if we go back and look at our initial sort of pictorial optimization formulation, where we had our equations explicitly available to us and we were able to plot them and show where the optimal solution is. Now we're looking at a case where all or a subset of equations are not going to be available in closed form. So our system is now represented with data, and we're trying to pinpoint the same optimal solution by looking at data. And that brings me to our current research directions within my research group. The very core capability we have is essentially data-driven optimization algorithms. That is something that I'm going to really focus on today and give you an application of that on supply chain management. But we're also interested in using these techniques for process control. So microalgae cultivation is something that can benefit from this. We also do more bread and butter type of process design studies with especially seawater desalination. And again, we have a really core program on more bread and butter data analytics, machine learning type of analysis for biomedical systems, essentially helping us to identify how certain biological functions are affected when you're exposed to certain chemicals. But today, we're just going to focus on supply chain management and data-driven optimization of these systems. Now, supply chain management actually requires the coordination of three distinct timescales. At the very bottom is that you have your longer term decisions, which is your supply chain structure. And on top of that, you have your planning decisions that are medium term type of decisions. And on top of that, you have short-term scheduling decisions that happen much, much faster compared to the supply chain. And there's this natural hierarchy, as you can see, for supply chain management. And when you're trying to solve these problems, the very intuitive way to do it is approach it sequentially. So what you do is first, you decide on your longer term decisions. For example, you decide where your facility locations would go on the map. You decide on your supply chain structure, essentially. And then you can determine your production goals by looking at the market demand and account for your inventories, decide how much to produce. Once you decide that, you take that decision and take it to your scheduling level, where at the scheduling level, you're trying to allocate your sources and you're actually trying to produce what you have decided at the medium-term decisions. You're trying to assign your tasks to the units. You're trying to schedule your entire production. Now, the sequential fashion is actually very popular, but it is also a little bit problematic. It is less than ideal. It's in the sense that these different levels of the supply chain decisions you have, they're actually interconnected because there are shared variables across these different layers. So here's sort of like a quick example of what happens. So this is a case where we have two products. We want to produce these two products and we have a demand profile. And this demand profile, assume that we have it for a week of planning period. Now, what you do at the planning level is that you look at these demand profiles and decide, I'm going to produce this much every single day for these two products. Now, these are your planning decisions, but you take these decisions without actually accounting your scheduling level, And then you go to the scheduling level, try to implement these production targets. And what happens is you cannot actually produce this much because you essentially, for example, over optimistically estimated your production targets to be very high to meet this demand. And when you come to the scheduling, you will realize that you're violating your capacity because you cannot produce this much in a given day. So at the end of this, you essentially have an unsatisfied product demand because you cannot produce this much at all. But what you can do, rather than the sequential approach, you can formulate this as a hierarchical approach. And bi-level programming essentially captures that natural hierarchy very, very nicely. So what you will do is you put your production planning level, and I'm just going to focus on just the bi-level optimization of it. I'm not going to talk about multi-level, so we're just looking at the integration of the planning and scheduling levels here. So we have the planning level as our higher level decisions. It's going to minimize our total cost of planning, subject to inventory and balance equations. And the scheduling levels are going to be embedded underneath this planning level. And you're going to notice in this formulation that there are shared variables across the planning and scheduling levels. Now, one thing that is very, very nice in the structure is that you're not just accounting for the objective function of each individual levels, but this also ensures that you do not run into violations in your scheduling levels. How is that possible? As you can see that this optimization problem is essentially a constraint on the upper level. You can see the subject to minimization of this. So unless you have a globally optimal scheduling level, you do not have a feasible solution for your bi-level problem. So this is a very neat and nice way of doing it. It ensures feasibility. But the problem is bi-level programming problems are very, very difficult to solve. Even the most simplistic case that you can think of, like a linear program constrained with another linear program, the resulting problem is strongly NP-hard. And the lower level problem is essentially yielding an overall problem that is non-convex. And this is a demonstration of how that happens. So we have a linear program constrained with another linear program. And since the optimality of this lower level is a constraint on the upper level, we can use the Karshkin-Tucker optimality conditions to reduce this bi-level problem to a single level optimization problem. And now we have our same objective function, but our constraints are now considering the KKT conditions. And you will notice that the complementary slackness is actually nonlinear. So if you plot your feasible region, you end up with this non-convex feasible region. So right off the bat, right, we had a linear program constrained with a linear program. Even these simple cases require global optimization because retrieving the solution of a non-convex problem is not so trivial. There's another problem that comes from scheduling formulations, and that is we have mixed integer formulations. So we cannot even use the KKT transformation to start with. I cannot simply reduce my bi-level planning and scheduling formulations with this trick. And on top of that, you can have your production demands to be stochastic. So you may have a good idea, but your product demands could be very, very variable. And you have to also account for the multi-follower nature of the integrated formulation. I'm going to come into the detail on why the multi-follower nature exists in a bit more. But essentially, when you're planning over multiple days, you have to schedule or you have to solve your scheduling problem for every single day. So it's not just you're following one leader and one follower, you have one leader but multi-follower structures. Now, of course, the difficulty of this problem also was quite an interest to the community. And this is just an indicative list of the previous works. And there are also more recent advances that are not listed here. But I want you to focus on looking at the solution strategy and different flavors that we can explore. For example, we can do branch and bound. You can get the epsilon solution, epsilon optimal solution with branch and bound. But unfortunately, branch and bound suffers with increasing number of variables when it comes to bi-level mixed integer optimization. You can do parametric optimization. You will get the exact solution, but you're limited to certain types of problems with parametric theory, so you cannot actually solve nonlinear, non-convex problems. You can use genetic algorithms, and genetic algorithms, again, they're data-driven techniques, and they're quite advantageous because you can actually solve certain types of bilevel mixed integer nonlinear programs, so they can address potentially these very complicated structures. But unfortunately, the feasibility nor optimality is guaranteed because genetic algorithms don't have a very robust way of handling constraints. You can use penalty functions, filter approaches, and so on, but you cannot absolutely guarantee the feasibility of your solution. So what we have asked ourselves is that, can we use a data-driven approach and different than a genetic algorithm to solve these BMI NLPs that contain a relatively high number of variables with a feasibility guarantee? And what we have worked on is what we call the domino framework. So we have this bilevel optimization problem given in this structure. We have continuous decision variables at the upper level, and we have mixed integer decisions at the lower level. And both levels can be constrained. And what we do within the structure, or even a more simpler bilevel programs, what we do is we look at the upper level dimensionality and we create a design of experiments on these upper level decision variables. You can use any type of design of experiments you would like. Maybe you have some sort of preference, or maybe you have your own design of experiments, you can use that. But the idea is when you create these design of experiments, you look at each of those samples and you fix them at the lower level. So for every X, you fix them at the lower level, we deterministically solve the lower level problem to global optimality. And in this case as well, you can use any type of deterministic optimizer that you would like. So if you have like a linear MILP, you can use Cplex. If you have more nonlinear or MILP type of problems, you can use Barron, Antigone, Lindo Global, whichever you prefer. And then this allows us to, once you get that Y star, this allows us to go back and evaluate our objective function and constraint violations. This essentially serves as our input-output data because we have our X, and now we have a corresponding objective function value and our constraint violations. And then we can pass this input-output data to a derivative-free optimization subroutine. Now, this derivative-free optimization subroutine, again, you can use different algorithms if you have preferences or ease of implementation. But this derivative-free optimization subroutine is going to continue adding new samples based on its sample selection strategies. It's going to check whether it meets the convergence criteria. And once it meets the convergence criteria, we will do two checks. One, we're going to check whether we satisfy all our gray box constraints. If not, then we have to go back and change our design. So we didn't have a feasible solution in this case. But if the answer is yes, then we have to do the final check. Remember that the lower level global optimality is a constraint on the upper level. So if the lower level is not solved to global optimality, we did not find a feasible solution. But if it's globally optimal, we do have a guaranteed feasible solution for the bilevel program. And as I said, you can use many different algorithms for the data-driven optimization step. So I'm showing you sort of the two ends of the spectrum here. One is NOMAD, Matched Adaptive Direct Search. This is essentially a pure sample-based strategy. It makes these compass moves to get close to the optimal solution. So it's like gradient descent without the actual gradients. And you evaluate your objective function throughout this. Or you can have more model-based structures. Maybe you have your own algorithm. I brought Argonaut as an example. This is something that I have also worked on. And what Argonaut does is that it builds individualized surrogate models for your objective functions and your constraints. So you essentially create the surrogate optimization problem by collecting this data. So for example, you can build these constraint regions and you can do bound tightening around them. You can use global optimization to solve the surrogate functions. But you can either, based on your preferences, you can either choose a sample-based strategy or a model-based strategy, which can also be local versus global. It really depends on your preferences. So we actually benchmark our framework with 4 different solvers, and we looked at the comprehensive test sets from the literature that we can find, and we evaluated Domino over 100 benchmark problems. And these problems varied in terms of flavors, linears constrained with linears, continuous nonlinear cases that could be, going from LP-QP complexity to NLP-NLP complexity. We also did mixed integer cases as much as we could find. Unfortunately, we are limited. These are very, very difficult problems, so it is hard to find these benchmark problems as well. But again, we tried different complexities at the mixed integer level as well. And our results have shown that we were actually able to identify near optimal solutions. So these benchmark problems with the known solutions, we were either was recovering that optimal solution, or we were very, very close to it. And all these problem types also vary in dimensionality, number of constraints, number of lower and upper level variables too. But I'm not going to go into the detail of the benchmarking, but I wanted to go back and revisit the planning and scheduling, because this problem is a little bit different than the benchmark problems that we had. In the benchmark problems, we had 1 leader, 1 follower, like a typical bi-level optimization problem. But in the integrated planning and scheduling, as I mentioned, you have a multi-follower structure. So you have your production targets at the upper level, and these are decision variables for our data-driven optimizers to Domino to recover. But at the lower level, if you're planning for 7 days, you have to solve your schedule for every single day. So you have to solve your schedule for each planning period. Then you have to account for your inventories. And those inventories essentially go to your upper level objective function calculation, and you would recover a total cost. And this total cost becomes your output. So you have your input, you have your output data, and you can use Domino to solve this problem. Of course, we have constraints, and I'm going to show you in a little bit more detail on what kind of constraints we have. But for example, you can think of things like inventories need to be positive. We cannot have negative inventories in our system. So that's one thing that we ensure also meeting the demand. And I'm going to first demonstrate some of the results on this quite famous scheduling problem. So this is a state task network of the scheduling problem with 3 different feeds. So we have feed ABC that goes into 4 different units, and you're trying to schedule 8 different tasks. And we actually are trying to produce 2 products. And we said, let's start with 7 planning days. And we created this demand profile. So this demand profile is completely synthetic. We wanted to start with something that will start low, peak midweek, and then dial down. So you can see that it's almost like a normal distribution in this case. And then we formulate our planning and scheduling problem. So what you have at the condensed representation is this. So we look at our planning level. Our total cost of planning is essentially what we have for our inventory and our production cost. Our inventory cost is however many inventory we carry times their price. And this inventory carrying for every single planning period actually depends on how much you produce at that day, plus anything that carried over from the previous day minus the demand you provide. So you write this balance equation to calculate your ending inventory. And we have constraints for essentially enabling cyclic planning. We consider cyclic planning because when you plan for the 7 days and you're trying to go to the next week, your task doesn't end, right? You start the next week. So if you have, for example, next week you have an inventory to start with on the first day, you need to be able to produce that at the final day too. So when you do just 7 days, your task doesn't end. You have to actually go to the next week and the other week and the other week. So we enable that cyclic planning in our calculations. And this essentially is actually a linear program on its own. Now looking at the lower level problem, now you have the production cost at your planning level objective, but this production cost actually comes from the scheduling level, and it is equal to the fixed cost of production plus any variable cost of material that you have. I'm not going to show you the entire set of equations, but this formulation has allocation constraints, storage constraints, duration, sequence, time horizon constraints, and material balances. We're actually using the continuous time formulation from Iropetra to Infludes in their paper from 1998. So you can refer to that if you're curious on the individual equations. But one thing that I would like you to bring your attention is this final bullet point. That is the production target satisfaction at the final event point. This is very important because this is how that interconnection happens between your planning level and the scheduling level. And here's how that looks like. So basically, at the end of the schedule and at the final time of the scheduling, you want your products that you produce exceed the production target you have, at least be equal, greater than or equal to the production targets you have. And remember that these were the decision variables that we had from our planning level. And this is how you do that interconnection. And your scheduling model in this case is going to be an MILP. Now we use Domino to solve this problem. So we have an LP-MILP formulation. And you're seeing the profiles for the first product over 7 planning days with 2 different solvers. The top solution is for Nomad, the bottom solution is for Argonaut. And the red bars show here the demand, orange is the production, and the gray one is the starting day inventory. So we would like this production and the inventory bars to essentially, their cumulative contributions should exceed the demand. And in all of these cases, if you eyeball it a little bit, you will see that we satisfy the demand for all planning periods. And the very most important thing is that the scheduling levels for each of the planning days is actually optimal. So this is guaranteed optimal. So we can guarantee that you will be able to realize this production. You will see that from the Nomad solution to Argonaut, there's a slight difference in the total cost. And this is basically because some of the decision variables are at a higher production level for Argonaut compared to Nomad. So the Nomad solution is a bit more tighter. And that essentially reflects on your higher costs that you see. And this is the profile for product 2, same idea. We see that both the production and the inventory actually exceed the demand for every single planning day. So demand is satisfied for all planning periods, and our scheduling levels are optimal for this case. And this is a little bit more clear. You can see that Argonaut chooses to overproduce in day 6 and carry an inventory, whereas Nomad is a bit tighter. You produce exactly on day 6, but overproduce 7, so that when you go back, this is where the cyclic nature happens. When you go back to the first day next week, you actually have that inventory to start with, and you can still meet this demand. Now, this was the LP-MILP formulation, but we know that Domino can do so much more. We know that we can handle nonlinear formulations. So what we wanted to do is, what if we actually considered our variable cost to be nonlinear? So in reality, the linear expression of the variable cost is just an approximation. Variable costs are nonlinear in nature. So what we did was that we took a quadratic variable cost function in scheduling, and we took a cubic inventory cost function in the planning level, and we created this NLP-MIQP formulation. And we resolved the same problem with the same demand levels. And what we have seen is that, again, we can satisfy the demand for all planning periods, and our scheduling levels are going to be optimal. What you're going to see is the stark difference in the total costs between the Nomad solution and the Argonaut solution. And this is primarily because of these little slight differences in the inventory carryovers from day 2 and day 3. So because you're now taking the cubic values of these, your cost difference is amplified. And if you look at product 2, same case, demand is satisfied for all planning periods, our scheduling levels are optimal. You can see that, for example, day 2 difference is a little bit more clear here. And these essentially translate into a higher objective function value. But regardless of that, whether you use a sample-based strategy or a model-based strategy within Domino Framework, you can actually get guaranteed feasible solutions for this problem. Now, we can also test the domino consistency, and this is what we have done. So the data-driven optimizers are sometimes could be very dependent on where they start, especially the local strategies like Nomad. So what we do is we start with different starting points. So we did 10 random initializations with Nomad, and we resolved our problem. And this is the results for the NLP MIQP. You can see that the error bars barely exist for product 1. You do see some variability here, but it's not more than I believe 30 unit material for these cases. But throughout the solution, what we see is there's a very low variability among the repeated runs. So we do actually have a very good consistency in converging to the same solution. So the confidence for getting the domino solution is also very, very high. Now, in these cases, right, our product demands were deterministic. Even though it was synthetic for us, we gave randomly some demand level, they were still deterministic, that we had one demand, we knew it throughout the week, and we tested that. Now we wanted to gear up and see what happens if our product demand was uncertain. Essentially, what if we have different kinds of scenarios for the demand, and how can we handle them? So we create these 10,000 scenarios, and we assume a normal distribution around their mean. And what we do is we're going to analyze in even a more simplified motivating example. So we start with 1 feed and 3 tasks and 1 product, and we're still planning for 7 days. So what we do is we sort of define these regions within 20% standard deviation around the mean, and we say, let's have low, medium, and high demand. And we're going to create scenarios for our planning days. So we're going to start with the first day demand known. Then we will go to day 2 and 3, and we're going to group them together and say that day 2 and 3 can be subject to low, medium, or high demand. Then for days 4, 5, 6, 7, we're going to group them as well and say these can be again subject to low, medium, and high demand. The reason why we did it this way, you can obviously do this grouping in many, many different ways. We wanted to limit the number of scenarios. We cannot test the infinite number of scenarios. So we randomly sampled 9 cases for these 9 different scenarios. So we start with day 1. And after day 1, you can have low, medium, or high day 2 and 3. And if you have low day 2 and 3, you can again have low, medium, and high day 4 to day 7. And the same idea repeats for medium and high levels for day 2 and 3. Now, I'll show you how these scenarios look like. So for this case, you're seeing the planning days and the demand levels. We start from the same first day demand, and you can see that how variable and how we capture these very different scenarios throughout our study. And one thing that I would like you to notice, even though when we mark or group our days, say that I want low or medium demand levels for days 2 and 3, they're not necessarily the same demand. We just sampled from the same region randomly, so they could be variable. As you can see in the blue one, day 2 is higher than day 3, or the purple one, you see day 2 is lower than day 3, and so on. So we're trying to cover a sort of a good spread of demand levels that we can see for our production. And of course, we would also need to change our deterministic formulation. So this was our condensed representation that we solved it once. Now you have to solve it per scenario, because now you have to calculate your total cost of planning for every single scenario that you have. And in more detail, right, we have to consider the occurrence of scenario probability. So we're trying to calculate a total stochastic cost of planning. In this case, we're taking them equal, but if you have real insight to the production, you can say that certain, occurrences are higher in probability or lower in probability, but in our case, it's essentially 1/9. Then you look at the total cost of planning, similar objective function. Now we just have to solve for per scenario. Then we have the same equations for the inventory cost. Again, they have to happen for now every planning period and every scenario. And you look at the scheduling model, we still have the continuous time formulation. We still have the same bi-level interconnection between our planning and scheduling. So we are still interested in producing more than the production targets we have, greater than or equal to the production targets we have. But we need to make sure that we satisfy this not just for one scenario, but for the entire set of scenarios and for the entire planning period. So this also necessitates for us to update how we execute Domino. Our inputs are still production targets. We are trying to solve our schedules throughout the entire planning horizon, but now we have to do it for every single scenario. You can execute them in parallel to save some computational expense. You need to account for your inventories per scenario, calculate your planning cost per scenario, then bring them together as a total stochastic cost of planning with your probability of occurrence for each of these scenarios. And this total stochastic planning cost essentially serves as your output. And now when you do that, this is for our motivating example, you see the data-driven complexity. We have 6 decision variables, and we have quite a bit of gray box constraints with a couple of few hundred constraints at the lower level. You will see that our solution is actually geared to our worst case scenario. When we had high demand for days 2 and 3, 4, 5, 6, and 7, throughout the week, we just have high demand. And since we're trying to figure out one production target and we don't know which scenario we will face, this makes sense that we at least satisfy the worst case scenario. And on top of that, if you don't face that, what happens is you're going to accumulate more inventory. And that's natural because you're sort of gearing your production targets for seeing a very high demand case. But for all these scenarios and for the entire planning period across all these scenarios, we satisfy the product demands and our scheduling levels are optimal. So that's actually a very promising result for us because you're solving now 9 times this very, very difficult optimization problem to get one feasible solution. Now, again, we assess the effect of initialization on the performance. You will see a little bit more variability compared to the deterministic case, but our standard error for our objective function value is actually very, very small. So we do see some variability here and there, but they do not exceed 27 units of material. So the overall consistency for Domino is essentially acceptable. And even for these 10 random initializations, even when we see variabilities, we actually don't have an infeasible solution. All these runs were completely feasible with scheduling levels that are solved to global optimality. Now, if we shift gears for a multi-product, now let's say you're trying to produce 4 more products in a more complicated scheduling structure, but still using the same idea of grouping and identifying low, medium, and high demands. What you will do is we will create individual scenarios for all these different products. Again, we're trying to create a nice spread here to cover all the possible possibilities that we may potentially see in our production or our planning level. And we run Domino for all these cases. Now our decision variable complexity is quadrupled. We have a couple of hundred gray box constraints that we need to handle at the data-driven level, and we have close to 1,000 constraints at the scheduling level complexity. And this is a big scheduling model to handle. But because we're using that deterministic optimization level, it actually helps us a lot to be able to address these problems. And like in the case that we have seen for the one product, so I'm just showing you the first product results here, we're actually very consistently find feasible solutions across all the planning periods. The demand is satisfied, scheduling levels are optimal, and there's definitely room for improvement. For example, there's this like very high carrying over of inventories, even at the worst case scenario. So that means that you have to actually produce a lot over the last day, but we know that this could be realizable through this structure. And we can show all these similar profiles for product 2, 3, and 4, but for the sake of time, I'm just showing product 1. Now, one other thing that we have done, and this is more tied into the performance of data-driven optimizer, is that how does the lower level complexity essentially relate to the performance of our data-driven optimization? So if you have sample-based strategies like Nomad, your sampling time becomes very, very important because that's your only way of getting information. And what you're seeing here for the motivating example and for the multi-product case study as well, these green bars are showing you the objective function value, the total stochastic cost of planning. So in the multi-product case, you will see that there's a drop. On the x-axis, you're seeing the number of event points in the scheduling formulation. So the effect of number of event points in the scheduling formulation is essentially increasing the number of constraints, number of variables that you consider. So you're increasing the complexity of your lower level problem by increasing the number of event points. And you can see that for the multi-product case, you can actually go up beyond 1,000 constraints at the lower level. Now, what we see is that initially, we see a drop in the computational expense of executing the scheduling levels. But as you make it more and more complex, your computational time increases a lot. And if you normalize it to the total number of samples that you collect, for example, for a motivating example, when your event points was 6 and you're within some moderate number of variables and constraints, it actually costs about 25 seconds to collect one sample. But with higher complexity scheduling levels, this almost it actually doubles and goes beyond. This is the same for the multi-product case study. It goes up to 121 seconds per sample. So the sampling time actually becomes very, very important. And we do parallelize it, and we are trying to benefit from the parallel computing capabilities. But 100+ seconds per one sample becomes very, very exhaustive, especially for algorithms like Nomad. But we wanted to go beyond, so this didn't really stop us. We wanted to go and solve scheduling problems with MI&LP levels, and MI&LP levels that we artificially did not induce. So in the first case, we made our variable costs nonlinear to make it a little bit more difficult. So we did have to change the problem type to be able to achieve that. And this is an example from crude oil operations. Very similar idea. So our vessels are going to carry oil, and you want to schedule sort of these vessels transferring their oil to storage tanks, and these storage tanks will then feed the oil to the charging tanks, and a blending occurs. The blending occurs because oil compositions vary widely based on where they're collected. So you're trying to mix two oils with two different compositions, and there's a demand that goes from these charging tanks to the crude oil distillation unit. Now, because this blending exists and because the compositions are different, you need to add component balance to your continuous time formulation. And that component balance is essentially nonlinear. So your scheduling model, even though the rest of them are integer linear or mixed integer linear expressions, your component balance introduces that nonlinearity, but you still have the demand from charging tanks essentially imposing bi-level feasibility. So our overall scheduling model here is MINLP. I'm not going to go into the details of the formulation, but we create this longer planning period for satisfying the demand in oil mixes. And we do have 2 oil mixes in this case. The only thing we paid attention when creating this demand is to not to have high demand throughout the 15 days. So we won't be obviously able to satisfy that. So we wanted something that goes up and down. But you see the complexity of the problem here. The data-driven complexity is about 28 variables. We have 62 constraints, and we have a couple of hundred constraints at the lower level as well. And since this is MINLP now, we're solving it with Baron. And here are the results. Again, we can actually satisfy the demand for these crude oil mixes, and each of the scheduling levels over the 15 days are optimal. We satisfy the product demand for the entire planning period. One interesting observation we had with the MINLP type of problems is that Nomad was able to find very consistent solutions to it. But even though Argonaut was a global approach, but being a model-based data-driven optimizer, it wasn't able to find a guaranteed feasible solution within 24 hours of running. So normally it was really, really fast in the previous cases, and we were able to get some close values for the Nomad. In this more complicated problem, we've seen that Nomad as a sample-based strategy actually did much, much better. And you can increase the complexity even more. You can have 3 charging tanks. That increases your data-driven decision variable complexity and the number of gray box constraints that you're trying to handle. You will also increase your lower level complexity. Now you're trying to solve thousands of constraints in an MINLP scheduling problem. So that's a very difficult problem to solve with. In this case, we limited ourselves to 7 planning days, but again, create these random demand profiles, solve it with Domino, and you will see that again, we can satisfy the product demand across the entire planning period with each of these schedules that are being optimal. Now we did, for this case, we did see one infeasible run recorded by Nomad. Now, as the complexity is substantially has substantially increased compared to the LP-MILP type of scheduling formulations, this is somewhat expected. And Argonaut couldn't even find a solution for this case within 24 hours. And with that, I would just like to share some concluding remarks. We have developed and extendedly tested our Domino framework, which is a bi-level multi-follower mixed integer nonlinear programming solver. And what our unique feature with Domino is that we're still approximating these bi-level optimization problems with to a single level optimization problem, but we do this in a data-driven way. We collect samples at the upper level, and we fix them at the lower level and solve the lower level problem to global optimality. And we tested this framework on a bunch of case studies, from benchmark problems to different type of scheduling problems, integrated planning and scheduling problems, to a very complicated MINLP crude oil operations case study. And we were able to provide guaranteed feasible solutions for all. One thing that I would like to note is that we are trying to speed up the algorithm. So the sample collection becomes very, very important for sample-based optimizers like Nomad. It affects the consistency. And we would also like to revisit the stochastic formulation for the more complex scheduling problems we had. And with that, I would like to acknowledge my graduate students. Hassan especially led this work, and our funding sources from different places. And I will also like to acknowledge our collaborators, Professor Siliana Avramidou from University of Wisconsin-Madison, and Professor Vasilis Haritopoulos from University College London. And finally, I would also like to acknowledge the Department of Chemical and Biomolecular Engineering at UConn. They have been an amazing support. It's really was a pleasure to do this work here. So with that, thank you so much, and I can take any questions you might have.
Thank you. Thank you so much for the wonderful talk. Nice, nice, very nice. So let's have a Q&A sessions. If you have any questions, please unmute yourself and ask questions. While you are thinking of your questions, maybe I can ask my questions. So this is data-driven, and you relying on the sampling. And how many data, do you have to generate
So,
usually?
yeah, so it really depends on the scale of the problem. Some of them are, I would say, a couple of thousand, but it is adaptive, right? The optimizers are trying to build confidence
Right.
in their solutions. But for more complex problems, it could go up to, 10,000 samples if you can
Oh,
afford it, obviously.
right.
So that's why I say sampling is a bit important, and that's why we're trying to work on speeding up the algorithm.
What sampling algorithm have you used so far?
So Nomad essentially works as its own because it's sorry about that. So it's evaluating these samples on its own. For Argonaut,
Adaptively.
for Argonaut we had Latin hypercube design, and the way that algorithm works is also adaptive. So you're building these surrogates, you optimize them, those optimal solutions become new sampling points, and you keep iterating. And the Argonaut one, because it's model based, it's more sample efficient. So you can get away with, a couple of hundred or a couple of thousand in the worst case. But because Nomad is more sample driven, it does collect a lot of samples.
I see. Well, you have shown this, application of this algorithm to supply chain, which has broad applicability, especially in industry. I'm sure here, Lawrence Livermore, we are very interested in those supply chain as well, because everything is about the process engineering, right? Are you actually work with any industry partner and showing this algorithm and apply this in real life problems?
So not yet. It would
Not
be
yet.
awesome. Yeah, not yet. It would be awesome to really team up with industry.
Yeah.
The initial sort of idea actually came from food energy water nexus. So that's also a very interconnected problem that you can formulate with a bi-level optimization problem. And then we wanted to go to more complex supply chain analysis. So I think that's naturally how it evolved, was from a different problem type to start with. But it would be super interesting. I know that the industry scheduling problems are far more complicated, and far more difficult to solve.
Yeah, for example, like Amazon would be very
Yeah,
interested.
yeah, yeah.
And also another application like flight scheduling, like the air.
Exactly.
They
Exactly.
will be very interested in
Yeah.
this work. I'm sure there are. I'm not personally working on the supply chain
Yeah.
problem, but I'm sure there are many people who work on the problems related to the supply chain in Lawrence Livermore as well. So feel free to reach out to Borku and do the collaborations. That would be awesome.
Yeah.
Well, since I'm not working on the supply chain, I'm more like the physical simulation guy. And in the optimization setting, as you know, like those sampling, individual sampling takes a lot of time. So you have to solve
Yeah.
one full simulation and sometimes just one fold simulation takes 1 week, even using the HPC machines we have here.
Yeah.
So yeah, I mean that. Any idea?
Yeah.
Extending this
So,
to
yeah.
PD constraint optimization?
Yeah. So, I think,
I had to ask this question because
yeah, I know. So when we initially worked with Argonaut, not in a bi-level setting, but we worked with a very expensive reservoir simulation. So one sample was like 300 seconds, and that's even a lot. So one thing that you can do is you can pick your so first of all, model-based data-driven optimization is going to be much better because they're going to be more sample efficient because you now have this surrogate that will help you, and you can use more interpolating functions like kriging or radial basis functions that are more sample efficient. So you can build relationships with a couple of hundred points. But now, seeing a little bit more development on the symbolic regression side, you can also use more like pins or symbolically regress type of expressions to alleviate some complexity. Essentially, you can create a surrogate of your simulation that you're going to have high confidence about, and use that, do this over that surrogate. But obviously you want some extrapolation capabilities and whatnot. That's why I sort of recommend doing these more physics informed or hybrid type of machine learning models. But I think that is possible to circumvent that issue.
yeah. Well, that is a good answer. I mean, even physics-informed neural network or symbolic regression, there are so much research needs to be done, but yeah, that's definitely one good directions to pursue. Well, is there any questions? I think I gave you guys plenty of time to think about question. If not, well, let's thank our speaker, Boku, for the wonderful talk, and really hope that there will be, future collaboration between you and Lawrence Livermore, if not Lawrence Livermore, with other industry people. This is very useful stuff.
Thank you so much. It was a pleasure.